Hi everyone, welcome back to this video series on Bitcoin. Bitcoin addresses. A Bitcoin address is a string of digits and characters that can be shared with anyone who wants to send your money. Addresses produced from public keys consists of a string of numbers and letters beginning with the digit 1. Here's an example of a Bitcoin address. 1J7MDG5RBQY UHENYDX39WBWK7FSLPEOX. The Bitcoin address is what appears most commonly in a transaction as the recipient of the funds. If we compare a Bitcoin transaction to a paper check, the Bitcoin address is the beneficiary, which is what we write on the line after pay to the order of. On a paper check, the beneficiary can sometimes be the name of a bank account holder, but can also include corporations, institutions, or even cash. Because paper checks do not need to specify an account, but rather use an abstract name as the recipient of funds, they are very flexible payment instruments. Bitcoin transactions use a similar abstraction, the Bitcoin address, to make them very flexible. A Bitcoin address can represent the owner of a private public key pair, or it can represent something else, such as a payment script, as we will see in pay to script hash P2SH on page 151. For now, let's examine this simple case, a Bitcoin address that represents and is derived from a public key. The Bitcoin address is derived from the Bitcoin address is derived from the public key through the use of the one-way cryptographic hashing. A hashing algorithm, or simply hash algorithm, is a one-way function that produces a fingerprint or hash, or an arbitrary sized input. Cryptographic hash functions are used extensively in Bitcoin, in Bitcoin addresses, in script addresses, and in the mining proof of work algorithms. The algorithms used to make the Bitcoin address from a public key are the secure hash algorithm SHA and the race integrity primitives evaluation message digest, specifically SHA-256 and RIPEMD 160. Starting with the public key K, we compute the SHA-256 hash and then compute the RIPEMD 160 hash, as a result producing a 160-bit 20-byte number, a RIPEMD 160 SHA-256K. Where is the K in the public key? The A is the resulting Bitcoin address. Bitcoin addresses are always almost encoded as base 58 check, see base 58 and base 58 checkup encoding page 66, which uses 58 chapters on a base 58 number and a checksum to help humanly readable, avoid ambiguity, and protect against errors in address, transaction, and entry. Base 58 check is also used in many other ways in Bitcoin. Whenever there is a need for a user to read and correctly transcribe a number, such as a Bitcoin address, a private key, an encrypted key, or a script hash. In the next section, we'll examine the mechanics of base 58 check encoding and decoding the resulting representations. Figure 4.5 illustrates the conversion of a public key into a Bitcoin address. Base 58 and base 58 check encoding. In order to represent long numbers in a compact way. Using fewer symbols, many computer systems used mixed alphanumeric representations with a base or radix higher than 10. For example, whereas the traditional decimal system uses the 10 numerals 0 through 9, the hexadecimal system uses 16, with the letters A through F as the 6 additional symbols. A number represented in hexadecimal format is shorter than the equivalent decimal representation. Even more compact base 64 representation uses 26 lower case letters, 26 capital letters, 10 numerals, and 2 more characters such as plus and forward slash. And to transmit binary data over text-based media such as email, base 64 is most commonly used to add binary attachments to email. Base 58 is a text-based binary encoding format developed for use in Bitcoin and use in many other cryptocurrencies. It offers a balance between compact representation, reliability, and error detection and prevention. Base 58 is a subset of base 64, using upper and lower case letters and numbers, but omitting some characters that are frequently mistaken for one another and can appear identical when displayed in certain fonts. Specifically, base 58 is base 64 without 0, number 0, O capital L lower L, I capital I, and symbols plus and forward slash, or simply it is a set of lower case and capital letters and numbers without the 4, 0, O, 1, I. Just mentioned example 4.2 shows the full base 58 alphabet. To add extra security against typos or transcription errors, base 58 check is a base 58 encoding format frequently used in Bitcoin, which has a built-in error checking code. The checksum is an additional 4 bytes added to the end of the data that is being encoded. The checksum is derived from the hash of the encoded data and therefore can be used to detect and prevent transcription and typing errors. When presented with base 58 check code the decoding software will calculate the checksum of the data and compare it to the checksum included in the code. If two do not match, the error has been introduced and the base 58 check data is invalid. This prevents a mistyped Bitcoin address from being accepted by the wallet software as a valid destination, an error that would otherwise result in the loss of funds. To convert data and number into a base 58 check format, we first add a prefix to the data called the version byte, which serves to easily identify the type of data that is encoded. For example, in the case of a Bitcoin address, the prefix is 0, 0x00 in hex, whereas the prefix used when encoding a private key is 128, 0x80 in hex. A list of common virgin prefixes is shown in table 4.1. Next, we compute the double SHA checksum, meaning we apply the SHA 256 hash algorithm twice on the previous result, prefix and data. Checksum equals SHA 256, SHA 256 prefix plus data. From the resulting 32 byte hash to hash, we take only the first 4 bytes. These 4 bytes serve as the error checking code or checksum. The checksum is concatenated, appended to the end. The result is composed of 3 items: a prefix, the date, and a checksum. This result is encoded using the base 58 alphabet described previously. Figure 4.6 illustrates the base 58 check encoding process. In Bitcoin, most of the data presented to the user is base 58 check encoded to make it compact, easy to read, and easy to detect errors. The version prefix is base 58. Check encoding is used to create easily and distinguishable formats, which when encoded in base 58 contain specific characters at the beginning of the base 58 check encoded payload. These characters make it easy for humans to identify the type of data that is encoded and how to use it. This is what differentiates, for example, a base 58 check encoded Bitcoin address that starts with a 1 from a base 58 check encoded private key WIF that starts with 5. Some example version prefixes and the resulting base 58 characters are shown in table 4.1. Let's look at the complete process of creating a Bitcoin address from a private key to a public key, a point of the elliptic curve to a double hashed address. Finally, base 58 check encoding. The C++ code in example 4.3 shows the complete step of the process from the private key to base 58 check encoded Bitcoin address. The code example used the LibCoin introduced in alternative clients, libraries and toolkits on page 51 for some helper functions. So here we go. Here's example 4.3, creating a base 58 check encoded Bitcoin address from a private key. So it's pretty lengthy, so I won't read all this, but you can look at it there and get a good idea. The code uses a predefined private key to produce the same Bitcoin address every time it is run, as shown in example 4.4. Example 4.4, compiling and running the ADDR code. Key formats. Both private and public keys can be represented in a number of different formats. These representations all encode the same number, even though they look different. These formats are primarily used to make it easy for people to read and transcribe keys without introducing errors. Private key formats. The private key can be represented in a number of different formats, all of which correspond to the same 256-bit number. Table 4.2 shows 3 common formats used to represent private keys. Different formats are used in different circumstances. Hexadecimal and raw binary formats are used internally in software and rarely shown to users. The WIF is used for import, export of keys between wallets and often used in QR code, barcode representation of private keys. So table 4.2, private key representation encoding formats: raw non-32 bytes, hex non-64 hexadecimal digits, WIF 5, base 58 check encoding base 58 with version prefix of 128 and 32-bit checksum. WIF compressed K or L as above with added suffix 0x01 before encoding. Table 4.3 shows the private key generated in these three formats: hex 1E99423A4ED 27608A15A 2616A 2B0E9E 52CED 330AC 530ED CC32 C8FF C6A 526AEDD WIF 5J3MBBAH 58CPQ3YRNJP UKPE625 Q5 TFCVU2 JPBNKEYHFSYB1JCN WIF compressed KXFC1JMWWCOA CICAW Z3EXA96BM6TB3 TYZGMF6Y WGDGWZGAWRTJ. All of these representations are different ways of showing the same number, the same private key. They look different, but any one format can easily be converted to any other format. Note that the raw binary is not shown in table 4.3 as any encoding for the display here would, by definition, not be raw binary data. We use the WIF to EC command from Bitcoin Explorer to show both the WIF keys represent the same private key. So here's the same private key here. Decode from base 58 check. The Bitcoin Explorer command C appendix G make it easy to write shell scripts and command line pipes that manipulate Bitcoin key addresses and transactions. You can use the Bitcoin Explorer to decode the base 58 check format on the command line. We use the base 58 check decode command to decode the uncompressed key. So here you can see, here's the key here. So the results contain the key as payload, the WIF version prefix 128 on the checksum. Notice that the payload of the compressed key is appended with the suffix 01, signaling that the derived public key is to be compressed. I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.